Welcome back. In the last video we have seen what is the Fourier transform of Heaviside function. Heaviside function is a piecewise continuous function, and we have seen that its Heaviside function is basically 1 by I xi root 2 pi 1 over I xi root 2 pi plus some Fourier transformation of constant function half. But as such, if you directly calculate the Heaviside function, see that is integral 0 to infinity 1 by root 2 pi e power minus I xi x dx. This is actually definition of Heaviside function. So, this is actually this integral is not in the usual sense, it is not defined. It is not defined. So, in that sense is actually you do not have this h cap of xi. It appears as a direct definition, it is not a usual function. So, that is expected clearly because this this integral value is integral is not converging integral. Okay. So, we have done in a different way. So, what we have done is we consider h of x as a limit of some functions, usual functions h alpha x, and then you calculated this h cap of thing, and in the process formally we have done, we brought this limit outside from this, and which is not really legitimate, appears to be legitimate, and if you have done you get this much, but if that is, if you assume that this is actually the result, you take the inverse transform of this, what you got, it should be your Heaviside function, but that is not the case. So, but what instead what you got is h of x minus half. So, what you should get is the h of x minus half whose Fourier transform is this one 1 over I xi root 2 pi. So, to get the Fourier transform of Heaviside function, so we can just take Fourier transform both sides again, because Fourier transform is basically you can go and come back through Fourier and its inverse transform. So, you can just apply both sides, so get this one here, and this right hand side is this, and you have this one. So, in any case what is that, if you directly apply the definition, you are not seeing that this does not integral does not converge, that means you expect this Fourier transformation of Heaviside function as is basically some generalized function. Okay. So, that is what actually we are going to get. So, and now we have to see what is the Fourier transformation of half, or simply calculate 1 first. Fourier transformation of 1 is again 1 by root 2 pi integral 0 to minus infinity to infinity e power minus I xi x dx, right. So, again this does not converge, this is not a convergent integral. So, you expect a Fourier transformation of 1 is some again some generalized function. Okay. So, I start with Fourier transformation of delta function of, so once you have the Fourier transformation of delta function, it is a function of xi, that is actually del cap of xi, and we have seen that this is 1 by root 2 pi is actually minus infinity infinity delta x e power minus I xi x dx. So, this is exactly this value, the function value at x equal to 0. So, that is 1. So, you have 1 by root 2 pi. So, so that means if you Fourier transformation of a delta function goes to 1 by root 2 pi. Okay. And if you do if you take the inverse transform of this, you get back your delta function. So, inverse transformation is instead of this, so you have 1 by 2 pi. So, this is 1 by root 2 pi, and 1 by root 2 pi e power minus I xi x dx is actually inverse transformation is actually delta x. Okay. So, this is what you have seen. So, that means if you start with delta xi as your some transformation. So, delta xi you consider Fourier inverse transformation of this, then it will be a function of x, which is by inverse transformation by definition this is going to be minus infinity infinity delta xi, because xi is a real number. So, we can do this delta xi e power I xi x d xi. So, this is inverse transformation of delta xi. So, this is also 1 by root 2 pi. So, this tells me now if you apply both sides Fourier transformation, what you get is Fourier transformation of 1 by root 2 pi is actually a delta function. Okay. So, this is a delta function of xi. So, this is actually what you have is Fourier transformation, yeah, fine. So, inverse transformation of this delta function, delta cap of it is not delta cap. So, you simply take the delta function as a function of xi. So, you have this one. So, this implies 1 by, so Fourier transformation of 1 is equal to root 2 pi into delta of xi. So, now this you go and substitute into your Heaviside Fourier transformation of Heaviside function, which is function of xi. Fourier transformation half will be half times Fourier transformation of 1, that is root 2 pi delta function of xi plus 1 by 1 over I xi root 2 pi. So, this is exactly what you have. So, finally, you end up the Fourier transformation of Heaviside function as root pi by 2 delta function of xi plus 1 over I root 2 pi into 1 over xi. So, this is exactly the Fourier transformation of the Heaviside function. So, you may come across these Heaviside function or delta functions in applications. So, when you have that time when you need to apply the Fourier transformation. So, these are the transforms that are useful. So, sometimes when you see that the Fourier transform of some function, if that integral does not make sense or it is not converging, it may basically it may be some, if you actually calculate, it could be some delta function, some generalized function. Okay. So, such as delta function. So, one such is the Heaviside function. So, we need only this Heaviside function delta function whose Fourier transforms. So, a Fourier transformation of delta function goes to 1 by root 2 pi, inverse transformation of 1 by root 2 pi will come back to delta function. So, directly if you calculate the inverse transformation of 1 by root 2 pi, which is 1 by root 2 pi minus infinity infinity 1 by root 2 pi, this is a function, and e power I xi x, that is the inverse transformation of this, which you think of delta function, right. So, this is actually 1 by 2 pi minus infinity infinity e power I xi x d xi. So, this is another form for delta function. So, another representation of delta function is, so you have this oscillatory function e power I xi x, if you integrate from minus infinity infinity, this is another representation of delta function. Okay. So, it actually tells you that if you fix x non-zero, and what you have is e power I xi x, which is oscillatory and which is oscillatory like sine wave. So, it gets cancelled. So, finally 0. It is a kind of weakly. So, that is the meaning of, say, because this equality is a weak thing. Okay. So, this is that way. So, generalized functions, when you say generalized function is this generalized function, so something is a generalized function, that means the equality is a weak equality. Okay. Delta has some representation which has the limit of some those. Okay. You get another representation for this delta function. So, with this we will just do some more problems, and also earlier I will try to do something. Earlier we have derived while doing a problem earlier in the earlier videos. Before I do this this thing, we have seen So, while doing this Fourier transformation of 1 over I xi root 2 pi, we have used this integral. So, this integral you can do many ways. You can evaluate this integral 0 to infinity sin xi x by x xi d xi. This value is depending on what value of x. If x is positive, this is actually pi by 2, if x is positive, and if x is negative, this is actually becoming minus pi by 2. That is what we have used here, and this is what we are going to show now. This we can actually do it by contour integration. I think after this Fourier transformation, before I do these applications of Fourier transformation, I will try to give you some, I will try to give the glimpses of complex variables, how to do the integration in a complex plane. I will do the contour integration. That is one way. One way you can do this, you can evaluate this integral by the contour integration technique, but now today we do only by Fourier transformation, because you know only Fourier transformation of some function maybe comes something, and when you fix those x values, you may end up getting this integral. So, through that way I will try to prove this result. We evaluate this integral sin xi x by x dx, okay, for xi. Xi belongs to R, okay, for different xi is positive or negative. So, we will try to show this one. What I do is, to do this, now not only we have a Fourier transform of a function, full Fourier transform, if the function is defined only for positive values, for example, this function sin xi x by x, this once you fix your xi, x is actually defined between 0 to infinity. So, this is defined only one side, 0 to infinity. So, you can use either cosine transform or sine transform for this function. So, let us start with, so to get this integral in some Fourier transform of something, let us do Fourier transform, Fourier sine transform of e power minus some ax, let us say a is positive and x is positive. Okay. So, it is defined only for one side. So, you choose such a thing. So, you have Fourier sine transform of e power minus ax of xi. This is a function of xi. So, this is equal to root pi by 2, or rather 2 by pi, right. So, what is that? We get this this Fourier sine transform, cosine transform, you have some coefficient. Even Fourier transform, you have a coefficient which we split into half as 1 by root pi. In the inverse transform is reflected as 1 by root pi. So, here we can get for Fourier sine transform root 2 by pi. Okay. We split that coefficient as root 2 by pi. In the inverse transform, it is root 2 by pi. So, without splitting also you can do, but the thing is, if I define without this coefficient, you have actually root 2 by pi integral 0 to infinity. This function is e power minus ax sin xi x, because it is a sine transform, and you have dx. So, this is your integral. If without this one, if I define in the inverse transform, you get you get the full coefficient, that is 2 by pi. Okay. Otherwise, if you put half of this here, so it will be reflected same coefficient you can maintain in your inverse Fourier sine transform. So, you can evaluate this integral, you see that it is 2 by pi. So, to avoid this, what is the integral you get? You can see that this integral is, do this integration by parts as an exercise. This is the elementary integral. We can easily see that it is going to be xi divided by xi square plus a square. So, how do I evaluate this? This is simple integral. So, e power minus ax sin xi x dx. So, you do one time integration. So, you see that is going to be e power minus ax by minus a sin xi x, you do it from 0 to infinity, minus plus. So, you have e power minus ax by a and you have this integral 0 to infinity e power minus a x, this you put it inside, and then you have to differentiate this sign. So, you have finally comes out as xi. So, cos minus a x, now sin xi x dx. Okay, this minus comes because your derivative of cosine is minus. So, finally, again here, so you have xi by a square here, infinity is part is 0. So, at 0 contribution this is simply 1 by a. So, you have this minus xi square by a square, this is actually your original integral. So, if you call this I, this is I. So, you have I. So, you can see that this is going to be 1 plus xi square by a square into I equal to xi by a square. So, a square goes. Okay. So, what you get is I is xi divided by this. So, that is how you can evaluate this integral. So, once you have this Fourier sine transform, what I do is I differentiate this because a is positive, a is defined, a belongs to between 0 to infinity. So, it is a differentiable function, you can easily see that this is a differentiable function, a is never going to be 0, it is 0 to infinity. So, I can differentiate this quantity, this integral. So, I will just from this what I get is 0 to infinity e power minus a x sin xi x dx is equal to xi divided by xi square plus a square. Both sides I differentiate with respect to a. On both sides we get what we get if you differentiate. This is if you differentiate with respect to a, you ignore this, this is an integral with constants. If you use the Leibniz rule of differentiation, so rule, there is a constant that is not 0. So, that parts 2 parts will be 0. So, only the derivative of with respect to a is minus integral 0 to infinity x e power minus a x sin xi x dx, which is equal to, and this one you can simply xi square plus a square whole square xi square plus a square differentiate with respect to a, that is 0, and you have a minus and you have a xi times into 2a if you differentiate xi square plus a square. So, this minus minus goes, and what you end up is Fourier sine transform. This is actually and you also multiply. So, you can take can keep this as it is root 2 pi if you want root 2 pi, and what you get up is 2 pi 1 by root 2 pi. What you end up is basically Fourier sine transform of x e power minus a x is equal to 2 xi a divided by root 2 pi xi square plus a square whole square. Actually, I think we have to integrate to get the result. Okay. The same thing, instead of differentiation, what we should do is integration. So, this is anyway, this is this really we really do not need, is actually why we should have done the integration. So, you this equality you do the integration with respect to a. How do I do this? So, let me write this, integrate the equality that means this one with respect to a from a to infinity. Then we get what we get, we can see. So, what we get is 1 by root 2 pi. If you integrate this from e power minus a x, what you get if you integrate e power minus a x by minus of that a minus divided by x. Okay. This is the integration of with respect to a. You are integrating dA, integration with dA, x y a variable. So, this one, and you are doing it from a to infinity. and sin xi x, this is as it is equal to 1 by root 2 pi, and what you here is you integrate from 0 to a to infinity, xi divided by xi comes out, which is not a function of this. So, 1 divided by xi square plus a square dA, that is the meaning. Okay. So, again so I can remove this 1 by xi both sides. So, what you get is, so if you see this is contribution is 0. So, you end up getting 0 to infinity sin xi x divided by x, right. So, you are substituting a equal to infinity, a equal to a. So, a you are substituting. So, in the place of a you put a, 1 is a. So, that is going to be e power minus a x divided by a divided by x. Okay. That is what you have. So, basically what you have is only at a equal to a contribution, that is minus minus plus. So, you have at a equal to a divided by x into sin xi x dx. If you keep these constants, these are actually Fourier sine transform of this function. This is equal to xi by square root of 2 pi, and here this is from a to infinity. You try to write xi by xi square, you take it out. So, you have 1 by xi goes here, 1 by xi, and you have dA by 1 plus a by xi whole square. So, what is this integral? Integral is, so you can take this 1 by xi also inside. So, d of a by xi you can put it, 1 by xi is a constant. So, you can write like this. So, this is, so if I write a by xi as x, 1 dx by 1 plus x square, integral a to infinity. Okay. Let me use in a more elementary way. So, a by xi, let a by xi equal to t, then that implies d of a by xi equal to dt. Okay. And what happens to your t? T is a by xi. When a equal to a, so you have, what happens to your integral is integral a by xi, and this is going to be infinity divided by xi. Xi is fixed constant. So, a by xi to infinity, and what you get is dt by 1 plus t square. So, what is this one? This is 1 by root 2 pi tan inverse of t from a by xi to infinity. So, what is this one? This value is 1 by root 2 pi tan inverse infinity is pi by 2 sin pi by 2. So, 1 by cos pi by 2 is 0. So, that is this one minus tan inverse of a by t is a by xi. Right. So, what I do here is, this is I allow as a goes to 0, I allow a goes to 0 both sides. What you get is this Fourier sine transform of or rather you see you cancel both sides if you want. Okay. It is not required anyway. So, 1 by root 2 pi, 1 by root 2 pi, all everywhere you can remove. So, what you as a goes to infinity, the left hand side becomes a to infinity sin xi x by x dx, which is equal to. Okay. So, you see that this is, here I have, when I substitute a by xi equal to t and I put this, when a equal to a by xi. So, this is a negative quantity if this is positive quantity if xi is positive. If xi is positive, a is infinity, this is going to be t is going to be infinity, that is fine. If xi is negative, okay, so this is where the difference is. If xi is negative, a by xi, that is negative quantity, and here infinity by xi, which is negative, infinity by minus xi, xi is a negative quantity, this is actually minus infinity if xi is negative. Okay. So, that is where you have to see the difference. So, if xi is positive, what you get is pi by 2, because and as a goes to 0, this is tan inverse 0. Okay. So, I have to write it here. So, this is going to be both plus or minus infinity. Okay. So, this is plus or minus infinity depending on if xi is less than if it is positive, this is infinity, this is negative, if I take xi is negative, this is going to be minus infinity. Okay. So, when it is tan inverse minus infinity, I should get plus if it is xi is positive, at infinity it is plus pi by 2, at minus infinity is actually minus pi by 2. So, that is what is the case. So, you see that clearly. So, if xi is this, so what you end up is, if you allow a goes to 0, this tan inverse a by xi, whether xi is positive or negative, this is going to be tan inverse of 0, that is 0, otherwise simply pi by 2 if xi is positive, minus pi by 2 if xi is negative. So, this is what it means. Okay. So, this is the result. You can actually this this evaluation of this integral you can also do by contour integration, and one way is just to pick up e power minus ax, x positive and a is also positive, and when you allow a positive, so you have to take positive side because a is positive. Okay. So, in any case you could evaluate this integral which you have used earlier to find some Fourier transform of 1 by I xi. Inverse Fourier transform of 1 by I xi you have used 1 by root 2 pi 1 over I xi root 2 pi. For that, if you wanted to calculate the inverse Fourier transform, that is where you have used this integral value. So, which we could show it by simple Fourier transformation of some simple function like e power minus ax, and then make use of this to evaluate this integral, that is the ultimate aim. Okay. So, we will do some more problems. Let me do some more problems now to find the, we will try to find Fourier transforms, and then using that we can show something. So, let us use let us start doing some Fourier transforms now. So, I will find the Fourier transform of the function f x, which is defined as if mod x is less than, let us say, some a, and 0 if mod x is greater than a. Such a function, so if you can easily plot, this is between minus, it is open interval, minus a to a, it is 1, otherwise it is simply 0. Okay, such a function, this is 0 and you have this is 0 and you have 1 here. So, such a function, how do you find the Fourier transform? And then deduce the value of integral 0 to infinity sin x by x dx. We can do this problem. So, solution. So, what is the Fourier transform of f x, that is f cap of xi. So, because 0 outside a, you have minus a to a, function is 1 e power minus I xi x dx. So, this is, and this is actually integral minus a to a cos xi x minus I sin xi x dx. Sin xi x in an odd function, so that is integral part is 0. This integral of that second term is 0. The only term remains is integral minus a to a cos xi x dx, which is divided by xi minus sin xi x, I think plus, right. If you differentiate this cos xi x into xi, so that xi goes, so what you have integrand. So, this is from minus a to a. This you get sin xi a minus of minus minus plus sin psi a divided by xi. So, this is actually 2 times sin psi a by xi. This is your Fourier transform. Okay. How do I get sin x by x? I think this is much easier, right. So, you try to take the Fourier transform of this function, maybe we are evaluating the same. So, you can express this one. In fact, you can get your sin xi x, right, sin a x by x, a positive or negative does not matter, right. So, we will see this one. So, a is positive. So, this is only restricted thing. So, we could do only for sin a x by x dx, a is only positive. Okay. So, if you use this Fourier transform, you could get only integral 0 to infinity sin xi x by x dx, xi is positive. Only part of this result you can get it, you can also get it from this Fourier transform. So, that is what it is here. So, if you take the inverse transform, this is the Fourier transform of this, and a is positive anyway, and you have the, to take the inverse transform, you have f x is actually Fourier inverse transform, that is inverse Fourier transform of 2 by xi sin xi a. I think I missed 1 by root 2 pi. This is my conventionally I defined it this way. Okay. 1 by root 2 pi, 1 by root 2 pi. So, you have by root 2 pi. So, this was the Fourier transform, and you take the inverse transform of this. By definition, again you have 1 by root 2 pi, and you have from now xi belongs to full real line. So, you have minus infinity infinity 2 divided by xi sin xi a, a is positive, into e power I xi x d xi. So, this is exactly divided by root 2 pi. So, this is 1 by 2 goes, so you get 1 by pi minus infinity to infinity. What you get is sin xi a by xi e power I xi x d xi is my f x. So, you can expand this and evaluate minus infinity to infinity sin xi a by xi, this is cos xi x dx plus other part minus infinity infinity sin xi a by xi I times. So, you have I comes out sin xi x d xi, this is d xi. So, you see that this is a real function, this is an odd function of xi, because the integral is from minus infinity to infinity. This whole function is, you have 3 functions, product of 3 functions which are odd. So, it is an odd function again. Okay. So, this is 0, this contribution is 0. So, you end up getting 1 by pi, and this is a even function. What you have is the even function here. So, 2 comes out 0 to infinity sin xi a by xi cos xi x d xi is my f x. Yeah, this is my f x. So, what is my f x? So, given what is your f x? 1 if x is less than a. So, if you allow x goes to 0, okay, allow x goes to 0 to get f of 0, which is equal to 2 by pi 0 to infinity sin xi a by xi cos xi x, as x goes to 0 is 1. So, you have d xi. So, you get f of 0 is 1, f of 0 is what? At 0 its value is 1. So, at this is 0, its value is 1. So, you have what you get is pi by 2. So, this integral sin xi a by xi d xi equal to pi by 2 and A is positive, that is what is given. Okay. So, there are many advantages just by using sine transform for Fourier directly. If you apply the transform for Fourier transform for this function, you can also show this sin xi x by x, part of it you could do. Okay. If you want a negative side, can we also get the same result, other result, that when A is less than 0. When A is less than 0, if you want how you define, you can define as minus 1 here. So, if you take this to minus 1, for example, if you take minus 1, what is the difference you get? Minus 1, if you do, you get this as a minus and A is positive. Yeah. So, this way you can do, you get a minus 1 minus 1 minus, so again I think you get the same, A is positive. No, you don't. So, you don't. So, you get the same, even if you whatever you take, you get the same, say part of this, only one part of this result you will get. So, by this same result you can get it from by many other by taking Fourier transform of many functions. Okay, so far what we have seen is either by applying a Fourier transform on a certain function or Fourier sine transform on certain function, we could evaluate certain integrals that we want. We can evaluate certain integrals using just by transformation, Fourier transformations, or it's that is for either direct Fourier transform, full Fourier transform, or sine or cosine Fourier transforms. Okay. So, we will see some more examples how to evaluate certain integrals just by using these Fourier transforms. Okay. Later on, so then we will move on to find the properties of the Fourier transforms and the main results, that is the Fourier integral theorem, which is done rigorously eventually. Okay. So, next few videos we will concentrate on that. We will see in the next video. Thank you so much.